in connection to Science Night. Please stand by.
Welcome back to another episode of the Science Night podcast. My name is James, and with me tonight is Steffi.
Hi.
And Jason.
Hello.
We've had a few weeks of special guest hosts, but tonight the team is back together again. And tonight the three of us will be talking about meat eating, frog legs, and solar storms. In the second half of the episode, we'll have my conversation with the artist slash bird nerd slash gamer who is also a very talented science communicator and planetary astrophysicist, the multifaceted, multi-talented Laci Brock. But first, the news. So if you've listened to this podcast in the past, you've heard us talk about how science is never really settled. New information lets us better understand the world around us, and sometimes the new information alters something that has been generally accepted for a really long time. And that is not necessarily the case right now with this first story, but it could potentially lead to that in the future. So for decades, the evidence available to us has suggested that humans evolved a disproportionately large brain due potentially to the addition of meat to the diet of Homo erectus about 2 million years ago. However, the team of Dr. Andrew Barr from George Washington University and friend of the show, Dr. Brianna Pobiner from the Smithsonian Institution's Human Origins Program, have discovered that explanation may be a little bit oversimplified, especially when we're talking about the evolution of our diet. Their very recent article in the Proceeding of the National Academies of Science may be the beginning of a new understanding on what made us human. So what do we think about this? This is like one of those things where this could be the beginning of a big change, or it could just be another thing that makes us look at the whole picture a little bit closer.
This is so cool. I'll tell you what I thought was the best part of this story was this pull quote that I saw from Brianna that talked about how she loves the idea of overturning conventional wisdom, especially when it's conventional wisdom that's attributed to her. Or that she subscribes to, right? And that, to me, was awesome. Like, here you are, a scientist at the leading edge of this particular field, pushing the envelope and trying to overturn your own positions. To me, that is the spirit of science altogether. I think what's interesting, though, about this particular story is really that it's a call for more work, more than anything else, because the authors have argued that the reason that we think meat eating was so important might be attributed to a sampling bias problem. So we've sampled fossils from, particular sites over and over and over again because we know that there's something interesting there, like butchery marks on bones or signatures in the enamel surfaces of the teeth of those fossils that suggest that they were eating meat, stuff like that, and not going to other sites and doing the same detailed level of work to try to confirm that hypothesis. And so this story really just says, hey, we really need to sample a much larger distribution of fossils at sites and see whether or not we can confirm the idea that meat eating was really important for the evolution of our expensive tissue brain. And that's an interesting idea too, right? The brain is such an expensive tissue to maintain that you have to put all of this extra energy that you can get from eating meat into it in order to help it grow. And so, calling for sampling at other sites is important, but we don't have a definitive answer to this yet.
I was just surprised. I didn't realize that even at rest, a human brain consumes 20% of the body's energy. That's amazing.
Yeah, you can kind of lose weight by just hanging out for a little bit. You're using that much energy. And I think one of the things like Jason was getting at with the expensive tissue is that could be one of the reasons that our intestines are so simplified as far as some of the other primates. The other thing that takes a lot of energy to upkeep is a digestive system because you're constantly replenishing it. So one of the thoughts is like, we have a big brain, we can't have a big digestive tract. Cooking, eating these calorie-rich things, like the addition of meat and honey to our diets, like all of this kind of goes toward paying off that energy debt by having this really big brain.
I agree with you. I think it's also important to understand that, while there may be a trade-off between a really expensive intestinal tract to run versus a really expensive brain to run or to power with energy, the reduction in complexity of the human gut tube relative to our most closely related primate species like chimps and gorillas might actually be more reflective of the types of foods that we're eating, as you sort of alluded to, James, and not necessarily related to it being too expensive to maintain in addition to a really expensive brain. And so, the idea here is that if we're eating substances that don't require additional breakdown, like leaves or flowers or even fruit, but we're eating more protein-rich diets, that we can actually process that a little bit better in a more simplified gut tract than we would need to process the high degrees of cellulose that you find in leaves and that sort of stuff. And so, you don't need as long or as complex of a gut tube to break down the more protein-rich diets. It's an interesting idea, and there is some idea about this trade-off between the expensive brain and the expensive gut tube, but it might just be an issue of the types of foods that we're eating, right? So there are so many questions that can be answered, and the authors are right. We need to sample more sites in order to have a good understanding of sort of what's going on. But I would say at this point, we have a pretty good understanding based on what we know of what's going on. And the question is, can we continue to confirm that, or is something new going to overturn it? And that gets at this question about, is the absence of evidence the same thing as the evidence of absence, right? And it's probably not the same thing.
Yeah. I still think finding more of the fossil record to kind of fill in those puzzle pieces is a really good thing, and maybe it leads to a confirmation of this theory, maybe it doesn't, but at least the net gain is there where, if we look at more locations and we find out more about the distribution of Homo erectus, maybe learning a little bit more about these new species that maybe it's just better to link to them as well than just do a big explanation. But things like Homo floresiensis and some of the other island species that we found, to find out a little bit more about them. So again, maybe we're not confirming or throwing water on this story, but at least it's the thing that gets us to look in more places rather than kind of revisiting the same sites over and over. Really, at the heart of it, what this article is calling for.
And to add to that, James, and some of these sites have been sampled differently than other sites, right? And so to make sure that we have tried to answer the same questions at multiple sites, as opposed to using one site to say, oh, this is evidence of meat eating, and this other site here where there may or may not be evidence of meat eating, we don't know because we haven't really looked at it through that lens yet. And so making sure that we've looked at everything sort of through that same prism will help us understand a little bit more. And then in addition to that, expanding the number of sites that are out there, right? So, you got to find the right age rocks in order to excavate, but they're all over the place.
How many main sites are there where people go to right now?
A lot.
Okay.
There's more than what I said.
Yeah.
The ones I listed are all in Africa. Ones in South Africa, 2 are in Tanzania. But there are sites in Europe that are looking at older species, like from the Miocene, which is an era before when you get to Australopithecus and our genus. I've heard that potentially India is underexplored and other sites in Asia are underexplored. I don't know so much about that, but I think now that we have a little bit more technology, that maybe we can identify these sites in a different way than just doing shovel tests everywhere. It might be the time to kind of broaden that net. But specifically the number of sites, I don't know.
Okay.
I could pick a number. It'll definitely be wrong. Jason, you probably have a better idea.
Nope, you're 100% correct. You'd be wrong. Whatever number you chose, it would be wrong.
Yeah.
Hundreds of sites.
Speaking of meat eating, later in this episode, we're going to talk to Dr. Laci Brock about how she's been able to blend art and science. And Patrick Pester, the author of the Live Science article for our next story, has painted a pretty vivid picture with his opening sentence, and I think Laci would be proud. And that sentence is, frogs can't naturally regrow their legs, but a drug cocktail did the trick. That is right. We're talking about frogs again, specifically the African clawed frog, which you may remember as the origin of the cell lines that went on to create the xenobots, which, as of recording, have not taken over the world. As the opening sentence states, a team from Tufts University have awakened a dormant regenerative capability in this species of frog using a combination of 5 drugs. So this group from Tufts is just pushing the envelope again. We got xenobots, we got frogs that can regenerate, we have a dormant regenerative capability in the cell line for the xenobots. Look at how we have this synergy happening right before our eyes.
There's a lot going on with frogs, it seems like. This is totally out of my field. Why do they do a lot of studies with frogs?
Frogs are a really good model system. So Xenopus is used, one of the genera of frogs is used a lot in developmental biology because the embryos can be manipulated pretty easily. And so they can understand sort of how limbs grow based on moving things around, right? I mean, there are some classic studies in frogs from the late 1800s, early 1900s that do some really weird things, or they take a part of the embryo and graft it onto another part and see what happens with development down the road. Because of that, a lot is known about how frogs develop. And so when it comes to vertebrate development, frogs are sort of one of the most prominent species that we know about these things from.
And I think we all remember the highest impact study using frogs as a genetic gap filler that took place in an island or a group of islands, I guess an archipelago off the coast of Costa Rica. I think it was Isla Sorna, Isla Nubar. So what happened is life found a way, and Jurassic Park.
I was hoping you'd go there.
You spent all this time wondering whether you could instead of wondering whether you should.
Spared no expense, though.
You know what's interesting? The thing that I never really understood is how it was that Newman from Seinfeld was unable to make that delivery. He's a mailman.
That's true.
That's his job. And yet he couldn't make the delivery of these embryos.
There were dinosaurs.
Watching that as a kid, though, the chubby guy with the steamed up glasses that just couldn't get his day to work out for him, that resonated with me way more than anything else in that movie. I was like, oh yeah, I know that feeling.
Guilty. So these frogs, this is crazy. This is so cool. I mean, so we know that amphibious vertebrates like salamanders can regrow limbs, but frogs are known to not be able to do that. Just like humans are not able to do that. And the hypothesis is that it's based on collagen development right away, or assembly, I should say, right away, that causes scar tissue in the place where the limb that needs to be regenerated was removed, whether that's by design in an experiment or whether that's by trauma and probably not an experiment, although there may have been something experimental going on that led to that trauma, not in a science perspective, however, just like being a stupid teen, I guess. We know that we can't regrow our limbs, and the idea that collagen could have something to do with that was an interesting idea. And so these researchers basically took this cocktail of 5 drugs, and one of which would prevent the assembly of collagen, and administered it immediately after removing a limb, and for 24 hours of treatment, right, where they basically took this little cap and they put it on top of this stump and said, okay, do your magic. They were able to regenerate limbs.
That was fascinating.
It's crazy, isn't it? I mean,
yeah.
So we know so much about how limbs develop because of frogs, and now we know that we can actually coax them to do that, or at least get them on the road to doing that. Obviously, this is not a perfect experiment. One of the things that the authors noted was that as they got down to sort of the furthest tips of the limb, the toe bones weren't fully formed properly, even though the limb itself could still be used to help generate enough propulsion within water that the frog could swim. We call this proximal and distal axis of development, right? Proximal meaning closer to the body and distal being further away. For example, our shoulder is more proximal than our wrist relative to our body. As these limbs are developing proximo-distally, something changes. And we actually know quite a bit about how that works from frog development already. And to me, that suggests that authors are going to need to sort of tweak what happens in later stages of development to see if they can then add a new cocktail of drugs to make the perfect, scenario that the foot can properly regenerate in the way that it's supposed to. And so, clearly that's the next step in something like this. But it's so cool that they can do this. I mean, we couldn't have done this 10 years ago by any stretch.
I just want to go back to the only 24 hours of treatment to get this process going. And it took 18 months to grow these limbs back.
Right.
I mean, that's amazing.
It's true. The whole time I was reading this, I was thinking of Deadpool. Right?
Yes.
Little tiny baby hand, right?
Oh. The whole time I was reading this, I was thinking, why did we choose this stem cell line to create these little organic robots with all of these hidden abilities? It's like, it seems like all the Xenobots have to do is eat enough little Xenobots, and they can level up and unlock a new ability.
Grow limbs.
Yeah, grow limbs,
Transformers.
grow brain. Exactly.
Grow opposable thumbs.
Oh no.
It's the stuff of nightmares.
Thanks, Tufts. Aren't you glad you read this story without knowing this was the Xenobot cell line?
Yeah, I just kept going back to the frogs that had teeth, and then now you bring in the robots.
Yeah.
Now I know there's a lot going on with frogs.
We better start training some dolphins a little bit better, I think.
Yeah. We need to bring back the what was it, the Navy the Navy program to weaponize dolphins and walruses.
Right.
And
or we need
oh my goodness.
The
we need
seals.
the Octonauts. Right. We need Bodie
Right?
McBoatface.
With
and
the seals.
Yeah. I'm less worried now. Bodie will keep us safe. Well, it wouldn't be a Science Night episode without a dollop of existential dread leading into the ad break. A solar storm occurs when the magnetic field of a star's atmosphere kind of clumps together and is pushed back into the star, which ejects Steffi's favorite state of matter, plasma, into space. And that plasma can wreak varying degrees of havoc on our modern, ultra-connected electronic world. And they tend to happen during a solar maximum, which is a period when the star is particularly active. However, a team from Lund University in Sweden has shown that a potentially crippling storm can occur really at any point in the sun's activity level, where the magnetic field is stable or unstable. And they've also revealed that we really don't know when these storms are going to occur, and that has left us incredibly vulnerable. So how does that make everyone feel? Just dandy, right?
I mean, this is kind of always happening. It just depends on which level. So we have a planetary magnetic shield. Magnetosphere is what it's called. And it traps these charged particles that are flying through from the solar wind before it hits the Earth. So when we really have to worry is when they get to these really high storm levels. So then that kind of leads us to protecting things like electronics, satellites, things like that, and predicting when these events will happen.
So can we do that? I mean, we really can't predict very well when these are going to happen, can we?
I'm not a solar scientist. We'll just put it out there.
You don't deal with solar science. You deal with the science of the sun, though.
On the Earth, yes.
Okay. Nice.
Yeah, yeah. So, I mean, there's a lot of scientists out there that are modeling, and then we have, satellites that are probes that are getting information, so you can get information from that. I just find what's going on in the sun fascinating. So you get magnetic reconnection, which is what James was talking about. So you get this tearing and reconnecting of magnetic field lines. Essentially, you're transferring magnetic energy to kinetic energy, which is shooting out these particles and magnetic field. It's kind of like if you twist up a slinky and cut it and it flings apart. That's kind of what's happening. And so it's just amazing what's going on in the surface of the sun. And then you put in the real life implications of those particles are going to go somewhere.
Right. So this story talks about how 9,200 years ago, I think it was, evidence of scarring on the Earth's surface from a major eruption of this plasma, hit Antarctica, right? And we see that. And what is really scary about that is that it happened during the solar minimum, right?
Yeah.
What happens if we're at a solar maximum, right? The idea here is that, there's a cycle with which these events occur, and this was happening when they weren't happening very often.
It's
And what
low
happens
activity.
if this happens when there's high activity? Exactly. That's going to be potentially really detrimental, especially since now we are even ever more reliant on electronics to communicate, right? So one of the points that the popular science story mentioned was what would happen in places that, are remote, but are relying on internet connections to maintain some sort of communication with a less remote place. And if that goes out, it could be months before they're back in communication. And what kind of havoc can that wreak on all sorts of systems that are in place here, right? Like healthcare systems and monetary systems and that sort of stuff. Like, could be really scary.
We're so connected and reliant on technology that we don't spend enough time to think of these scenarios on what are our backup plans.
Right. How are we going to do a science night recording if we can't do this on Zoom, right? We live in 3 separate states.
I mean, I guess we could wax cylinders and kind of mail it to each other.
Yeah.
Maybe we should do that anyway. We should prepare. And then we'll be ahead of the curve when this next solar storm cripples all planetary telecommunications.
So what you're saying, James, is we all need an emergency kit in our basement. And in that emergency kit, we need to have an extra podcasting mic and a hand-cranked battery-operated generator so that we can,
Or we can start shielding things.
Yeah, and also like an Edison brand wax cylinder recording device, a gramophone.
There you go. We can start burying power lines, shielding buildings.
Sure. I guess that's the real answer.
I think it's just a reminder everything can kill us or something like that.
Sure. Yeah, everything we've talked about today can kill us. So we've really got to get better at this. Maybe we should do like a solar punk story next episode where it's like cyberpunk but nice and bright and not post-apocalyptic. Speaking of angry stars, after the break we'll talk to Dr. Laci Brock that studies brown dwarfs as well as many, many, many other things. But first, a quick message from another show we think you might enjoy.
Nature, we're part of it. Animals, we're one of them. What can we learn from other species? How can our lives be better by reconnecting with nature? And why does it matter at all? That's what Wild Connection, the podcast, is all about. Every week, we bring you authors, filmmakers, scientists, and conservationists whose work is revealing why being connected to nature and wildlife matters. You can find us where you get your podcasts, including iTunes, Google Play, and Spotify. We're hosted by Podbean, so you can find us there too. And you can keep up with us on Twitter at WildConnectPod.
With us today is someone I am really excited to talk to. Dr. Laci Brock is an astrophysicist, an artist, science communicator, self-described bird nerd, a gamer. The list goes on and on and on. Laci, welcome to the podcast. I am so happy to have you here.
Hi, thank you for having me.
So we're going to start out with one of those seemingly deceptively really easy questions, but there can be quite a bit to it, and it's going to be really simple. Tell us about what you do.
What I do is I model the clouds on objects called brown dwarfs. They're colloquially referred to as failed stars because they're sort of this hybrid in between a planet and a low-mass star. But their clouds are made up of things that are really interesting, like clouds made of iron and gemstones, like sapphires or rubies. And that's what I study.
That is incredible. It is.
They're pretty cool.
One of the many reasons I wanted to have you on the podcast is I, as an anatomist, know very little, surprisingly, about astronomy, other planets. I know that they exist. I can kind of conceptualize that. And I know that the astro community is very excited now with the recent launch of the James Webb Telescope. So yeah.
So exciting.
It finally got there. You know, we just needed a little help from Santa to get it off the ground, and it got there. And my big question is, how the heck do you learn about these stars that are so far away?
What I use is, you can use large telescopes that are on the ground, like Keck in Hawaii is one of them, the 10-meter telescope. You can use Keck. You can also go to space. So Hubble and now JWST will be really helpful to study these objects. JWST in particular, because the objects are very faint. You can't see a brown dwarf in the sky with the naked eye, but they're very bright in infrared wavelengths, which is what JWST will specialize in. So that's why it's really exciting, because we'll be able to detect more and study the atmospheres better of these faint objects.
What are some of the things that you're really excited about learning now that we have the ability to detect more and fainter stars?
Well, there are so many things. Let me try to narrow it down here. One thing in particular is I model the clouds, and there are still a lot of uncertainties to the we can use our models and see, well, these are the different types of cloud condensates that could form in the atmospheres, but we don't really know how those clouds are layered in the atmosphere, or if there are even storms on them, sort of like Jupiter has the Great Red Spot. We think brown dwarfs could have banding like Jupiter, but we're not really sure. So with more data, it's always a lot better if you're a planetary scientist or an astronomer, because you can start to study these objects in more detail and narrow and refine your atmosphere models.
I want to generally talk about the science of planetary astrophysics and what that community looks like. And it doesn't seem like something one just stumbles upon. There has to be a story with how you got excited and really into this profession. So why don't you tell us a little bit about that?
I am one of those kids. I have the story. Oh, when I was 4 years old and I went outside and looked up and I just thought, oh, that's so cool. What is that? A star. I want to learn about it. I always was interested in space. When I was younger, I have sort of that cliche story. No one in my family went to college, but I sort of always knew I wanted to be a scientist. And I was a huge nerd. Like, I was in the driveway collecting rocks. I was really interested in volcanology. But most of all, I think I was interested in the weather. And so I initially wanted to study severe weather or be a storm chaser. And I read all these books when I was younger. And I went through high school, didn't realize I could go to college. I didn't know financial aid existed until I was 20. But then I finally figured out that I could get funding and I could get loans and I could go to college. And I started as an atmospheric sciences major with the intent of studying severe weather, chasing storms or something. But I also really loved space. And that had always been a big part of myself. And I really wanted to study clouds or weather on other planets. At the time, I was thinking, in our solar system, maybe Venus or Jupiter. But I didn't know planetary science existed until I was already a sophomore during undergraduate. The field had been around for maybe 50 years. It sort of branched off from astronomy and became more of a program that you could go to school or to grad school for. But I didn't know it existed because I was sort of floating around aimlessly through undergrad. Not only was I the first generation student, I started college when I was 21, but I was so confused. I had no idea. I transferred around to a couple of different colleges. But finally, sophomore year, I took an oceanography course for fun. And the professor and I were talking one day. He asked me what I wanted to do. And I said, well, I like space and I like atmospheric sciences. I kind of want to do both, but I don't know. And he said, well, hey, Purdue just got a planetary sciences faculty member named Dr. Jay Malash, and he was the first faculty member at Purdue. And my oceanography professor said to email him. And I emailed Jay, and that basically changed the course of my academic career, and that sort of got me where I am right now. And so I did undergraduate research for Jay, and I switched my major from atmospheric sciences to I think it was officially interdisciplinary physics, because the degree for planetary sciences didn't exist at Purdue yet. They got it, I think, 2 years, or the year that I graduated, it became an official category. But I started working with Jay on exoplanets and the idea of panspermia. We didn't have an atmospheres faculty member yet, but that was my plan. After getting this planetary sciences background at Purdue, I thought maybe I could go on to grad school and study brown dwarfs or atmospheres on exoplanets.
That is an amazing, twisting, turning story.
It's crazy ride.
Yeah, the kind of theme that comes out is you're riding the cutting edge wave the entire way. You know, first in your family to go to college, and then you're getting into this brand new program, this brand new department, and you're just finding your way through. And I feel like that is a very interesting story, and one of those that needs to come out a little bit more than the standard, like, oh, well, my family were scientists, so I did the science thing, and that's why I'm here right now. And
Yeah.
You can tell how much passion is behind my voice.
Yeah, I don't even think my dad knows what I do to this day.
You just got your PhD. You just defended your thesis. You are a doctor. It is
I
amazing.
guess so.
As I was following your path on Twitter, you could tell when the days were a little bit more difficult than others.
Yeah.
Why don't you tell me about your grad school experience? How did you make it? How did you get there? What were the things that kept you going and kept you into what you were doing?
Oh, well, okay. Hold on, because this is also another crazy ride. I graduated from Purdue, and, the last semester you apply for graduate school, and I applied to 9 PhD programs, and I got into zero PhD programs. I was really upset because I worked 3 jobs during undergrad, and I still had, a 3.4 GPA, and I had research experience, and I took classes every summer, and I worked so hard, and I didn't get into any PhD programs. My advisor, Jay, said that I should try to apply to a couple master's programs, and I didn't think of that. But I ended up getting into Northern Arizona University in Flagstaff for a master's degree in applied physics. So I went on to NAU for that master's program, and I was trying to find a research project. And there wasn't really something that I was clicking with. I just, in my gut, I didn't feel like these projects were of interest to me. I don't remember how, but I ended up talking to Dr. Dave Goulet of the Northern Arizona Museum, and he was the curator for geology and paleontology. And he had this idea that was connecting Earth's geological history with cosmological time in a museum exhibit somehow. And I thought, oh, this is perfect. I love interdisciplinary things, and I can't ever decide what I want to do. And so, wow, this is cool. And so I had taught before during undergrad as an undergrad TA, but this was a science education research project. And I thought, I'm going to do it, even though no one else in the department had ever done it before. But I decided to be the only physics astronomy grad student that I was going to do this science education project. And so I did that project, and I got more interested in science education. So then I still wanted a PhD because I'm stubborn. So since 4-year-old Laci decided she wanted a PhD and she didn't even know what that meant, she wasn't going to stop until she got it. So I applied to where I'm at now, University of Arizona, to get a PhD in science education. I get in the science education department because I'm going to do astronomy education. I get there and I don't like it. The department is just not as research-based, and I'm actually working in the Lunar and Planetary Laboratory, the department that I eventually graduated from. I'm working as a TA in that department because the education grad students didn't have any funding. So I had to find a job once I got there. I'm working in one department, I'm doing research in the astronomy department, and I'm taking classes in the science education department, and I'm just all over the place. And I decided that I needed to transfer to the Planetary Sciences PhD program. You don't really do that. You don't really transfer PhD programs. But I talked to everyone I was working with. I asked, can I apply to transfer because something has to change? Well, I applied and I got in, and I was in the education department for a year. Then I transferred And then I eventually graduated with my PhD in planetary sciences. But to make things more complicated on myself, I, of course, had to do something different. So I did a hybrid PhD. So a third of my dissertation was science education, sort of the work from my first master's. I continued that work on cosmological time. And then I did my work on brown dwarf atmospheres. So when I defended my PhD, I had a round of science questions, a round of science education questions. So every, the comps and whatnot during my PhD, I got grilled on science, then I got grilled on science education. So I made everything harder on myself, and whatever, it worked out. Here I am, but it was a crazy ride.
I think I am now finding out why you are so able to navigate the waters of social media and science communication and some of the negative things that come with that. As, you've been through absolutely everything. What more could possibly come your way?
I know. I didn't even talk about the car accident. There was a car accident in there too. Yeah, it was a great time.
You are tempered, for sure, at this point. I've mentioned your science communication. I want to pivot to the science communication that you do. As I'm finding out that you have this vibrant background in science education, it only makes sense that you would be able to find your voice and explain your science because, let's face it, sometimes your science is not the easiest thing to grasp for persons like me who look up and can identify that there are stars there. And then my daughter asks me something about them and I'm like, here's a video. Here's a video. It's a long time ago. And then, yeah. So what did you find that worked to make the more technical aspects of your work a little bit easier to communicate with people just from the general public?
A lot of my work in science education was sort of developing curricula. And so I'm better at developing curricula on paper than I am making a science communication video. But I tried to take the same principles that I learned from curricula development or research with undergraduate students to those videos. And the biggest thing is to leave out jargon. I don't like to use jargon at all. Sometimes I will use an astronomical unit, and a lot of people know what that is, but I will define it. So if I use any kind of term that is important for the message I'm delivering, I'll make sure to define even astronomical unit. I'll define it in the video as text because I want to make it accessible. I also try to use meters and miles or something because different audiences will watch my videos. And then all the people in the rest of the world are like, America and your freedom units. I'm like, they're like, well, you're a scientist. Why are you including this? I'm like, because it's accessible. I didn't decide to use miles. Like, don't put this on me. I'm just trying to make my video accessible. The other thing, I am still really uncomfortable and awkward when I make these videos. I sort of freeze up and I can't even, if someone asks me to explain my dissertation and just put it like a camera in my face, I still get very nervous and I freeze. So what I like to do is sort of break things down into key points. And so I'll say, here are 3 cool facts about Jupiter, and then I can give each fact with maybe another sentence. And that helps me keep it structured and keep my ADHD under control. And it also breaks it down into bite-sized chunks for whoever's watching my video.
All of the points that you made are really smart. We're very passionate here at the Science Night podcast about removing the jargon from any type of science communication and also really inserting yourself into your science. And I now want to talk about, maybe some of the less pleasant things that you do with your science communication, because you are very good at all of the things that you said, making your communication approachable to everybody, breaking it down into these digestible chunks to make it sticky and make it something that you can remember. And your comment section can still get a little bit wild.
Yeah, it can get a little silly in there.
What are some of the ways that you've come to just make yourself get through those moments?
I very quickly realized that I wasn't the bubbly, smiley, jump up and down and point to things science communicator, and that I was more of the sarcastic, sassy science communicator. And I would get people who would ask legitimate questions. But then I started getting conspiracy theorists that were just trying to yell at me, NASA lies and propaganda, it's all photoshopped. And I delete and block a lot of things, and I do that all the time. But not everyone on the internet is a troll. There are actually people who are very clearly misogynistic, and they have problems with women being in science or engineering. And I don't like that. And I decided that I was going to speak out against it. So if I'm not blocking and ignoring people, I will respond to trolls if I feel that it is important and there's a message that I want to deliver. So I will respond with amazing sarcasm. And then when I get flooded with a lot of conspiracy theorists or annoying comments, I just started trolling back. And so I just started responding, D's nuts. People would say, NASA lies, it's propaganda. And I would select one of the words that they use and then add D's nuts. For example, propaganda D's nuts. And I was cracking up. I was like, this is great. I am not upset now that I'm being flooded with these comments. I'm taking the power back and trolling back and laughing at them. And that ended up being content. And then I realized, like, well, people want to watch these videos where I troll back more than my science videos. What have I done? But the reason why I do it is because it actually makes me feel better about opening up the app. Because what people don't understand is when you tell somebody to just ignore, I don't have as many followers as other people, but I have 50,000 people following me. That's like my entire undergraduate college. I am deleting and blocking 99% of things, but I still have to open up the app and read the comment and delete it, then click on their profile and click block. So telling me to ignore something is actually more annoying than the trolls. But when I can just hit them with the D's nuts, it's really funny. And I smile as I block them.
The first thing I want to say is I'm really sorry.
Very mature.
Whatever gets them in the door, right? But, I want to say that it really sucks that you have to deal with stuff like that. And, I, because of the way I look and the person I am, rarely have to deal with that. And it is even worse that that's kind of the state of science and science communication and the world at this point. And I am also very glad, both for your own mental health and for my own entertainment, that you've found this particular pathway forward.
Yeah, I'm liking it.
You say it's snarky and it's sarcastic and it's more popular than your science communication, but it's the thing that gets people to follow you. So they come for D's nuts and they stay for the science, right?
I hope so.
You are, as I said in the intro, a very multifaceted person, and we could talk all night and not cover all of the things that you kind of excel at and have found your way in. But I really want to talk about your art and how you have used art as another way to explain your science and communicate, again, these very complex things in another media.
Can I tell a story really quick about my art? Okay, before I go into more detail. So I've always painted my entire life. I have been painting since I was 3 or 4. I don't know. I've just always painted and I've always been pretty good at it. When I was a senior in high school, and at this time I didn't know I could go to college, but I couldn't decide between science and art. I thought I had to pick. And I went to the guidance counselor and I told him this. I'm interested in science and art. And I'm sort of like careers in science and art, like together, or I want to be both. And I remember this because it sort of shaped some of my decisions later. But the guidance counselor tossed, I'm kind of old, so he tossed a newspaper across the desk at me and he told me to check the classifieds and look and see if I see a job for an artist. And I just sat there and looked. Wait, what? He's like, do you see any jobs for an artist? And so basically he implied, like, that's stupid. Why would you go to school for art? But then he didn't tell me how I could go to college to be a scientist either. So it was a worthless experience, but I got it planted in my head that I couldn't be a scientist and an artist. And so I eventually went to school for science, but I kind of disconnected with my painting. I would paint a little bit, but I really disconnected it from the science. I treated them very separately. But during grad school, your comps and everything gets very stressful. And I felt really empty and unfulfilled. Like I loved my research, but something was missing. So I took a painting class at U of A. I sent them my work and they let me take the painting classes at U of A without enrolling in the prereqs, because I wanted to learn how to paint in oils. I started teaching myself more mediums because I painted in acrylics my whole life. But I took the painting class, and my department actually had the Art of Planetary Science, a space-themed art show where artists from all around the world submit their work to. And so I started painting space art again and submitting my art to the art show, and then taking these art classes while I was doing all of my planetary science stuff. And I felt connected again. And I realized that I could do both. And why do I have to separate them? Like, that guidance counselor was crazy. Why did he tell me that? And here we are. And that's why I actually started my social media accounts for art. Mm-hmm. And then later I realized, well, I should add my art to it. It's been kind of difficult, though, to run an account that is both science and art, because people tend to have separate accounts for that.
One of my problems with that divide is that historically there hasn't been a divide between science and art, and historically meaning at the time of the Renaissance.
Back in the day.
Yeah. Now there definitely is. You're absolutely right. There is like this taboo of combining your science and your art and having it be just one persona. I think that in a world where science has got to find a way to communicate to the average person, that we should not be separating any of these methods. If you are able to excel at any way to explain your science, or to explain science in general, that should be celebrated, not pushed to the side. Absolutely.
Yeah, I totally agree.
Yeah, and this is also coming from a person who does not have an artistic ability. I guess my voice is my art, and I can paint with expression. There's also a reason I don't do video or anything like that. Purely a voice-based situation. We're finding that you've got a lot on your plate. You do a lot of stuff. And is there downtime in your life? Are there things that you've found a way to carve time out to enjoy just for you? Just things that, you can do other than work and science related?
Yeah, people ask me all the time, how do you balance all this stuff? And I stayed up until 6 a.m. 2 days ago playing video games. So I don't think, if I had to assess myself, I don't think I balance things very well at all. I think ADHD takes over my life, and the next thing you know, I'm playing games till 6 a.m. But I try to paint a little bit each week. I got an iPad a couple years ago, and I started teaching myself digital art. So I try to paint a little each week. I play a lot of video games. I play a lot of Apex Legends. I usually get on like every night, every other night, and play a couple hours with friends. I do that after work, and if I'm not painting, I still feel it's sort of like, do I want to play games or do I want to do art? Because I have some wrist problems, and I can't do both in one night. And bird watching, I haven't been in a while because I got a little busy finishing my PhD, but I like to go bird watching too. And that's sort of the way I disconnect and relax, walk around and listen for some birds.
I feel like I would not be doing my job and getting your message out there by not asking you if you would have any advice to the next generation of Lacis that are coming up and trying to find like this interesting path that they have in their head, but people are not making easy for them to find.
My advice would be not to listen to anyone. It's just carve your own path. It's not going to be easy. It's not going to be visible a lot of the times, but it doesn't mean it can't be done. If you want to do something, you can make it work in whatever way works for you. I mean, a hybrid PhD doesn't exist, but 2 other people did it in my department. And so it's possible, but no one will advertise it to you. So my advice is to be true to yourself and carve your own path. And Also, not to disconnect science and art. If you want to be a scientist and an artist, you can absolutely do both. You can connect them in multiple ways. Scientific illustration is a job, a graphic design. I've actually met a lot of other scientists on Twitter who even have their PhDs, and then they run an art business on the side. They sell space stickers or pins or socks. And so, your day job, if you want to do your scientific research, do it. And then at night, you can sell your art. You can absolutely be both. And that would be my biggest advice, because I think that if I wouldn't have listened to that guidance counselor back in high school, maybe I wouldn't have tried to push my art away for so many years. I think maybe I would have connected it to my life a little more throughout my school experiences.
Excellent advice. Laci, you have been so generous with your time. We're so happy to have had you here today. The last thing I am going to ask you is tell us how we can follow and support you. What can we do to make sure you're able to do your science and your art far into the future? Well,
thank you so much for having me. It's been a pleasure. I am on TikTok and Instagram and Twitter, and it's all the same handle. It's at Stellar Arts, but it's Stellar with an E. STELLER Arts. It's named after a bird I can spell. It's the Stellar's J. And Stellar Arts I was trying to think of a name to combine my love of birds and space and art, and Stellar Arts ended up being it, and it wasn't taken.
We will have links to that on our website. Laci, thank you so much. Thank you so much to Laci for talking to me. She is incredible, and we will link to everything she does on our website. That is going to do it for another episode of the podcast. If you want to follow me, I'm on Twitter at James_Reed3. Steffi, where can everybody find you?
You can follow me on Twitter at SteffiDM.
And Jason, where can everyone find and keep tabs on you?
Also on Twitter at OregonJM.
I can assume that we'll be seeing less football-related tweets in the coming weeks from you, but that's an unrelated story for an unrelated time. Follow this podcast at Science Night 1, and be sure to check out our website, scinight.com, for all previous episodes, links to the articles we talk about, and lots more. Also, be sure to rate and review us on whatever you're listening to right now. It really helps us break through the noise of the podcast world, and we would greatly appreciate it. Thank you so much for listening. We will be back in 2 weeks with a brand new episode, and until then, have a great night. The Science Night Podcast is a proud member of the Riverpower Podcast Mill. To find out more about our shows, go to riverpower.xyz.
I thought you were calling Laci Brock an angry star.
I mean, kind of.
I know. She's awesome.
She is.
I'm just going to keep that in so she can know how we feel about her.
See you next time.